Welcome students once again into the class of number theory, and in this video we will have some problems, some theorems related to Mobius function. What Mobius function is I have already defined, so let me define it once again because we are going to do many questions related to Mobius function now. So Mobius function is denoted by mu, and mu n is equal to 1 if n is equal to 1, mu n is equal to 0 if n is not square free. Not square free means some perfect square completely divides n. In that case, the value of mu n is 0. And the third case, if n is square free. So if n is square free, then n can be written as product of primes p1, p2 and so on, pr, and the value of mu n in this case will be minus 1 raised to the power r. R is the number of primes whose product is equal to n. So this is the definition of mu n, and now we will have some questions, some theorems related to this Mobius function. So first of all, the first theorem is that mu n is a multiplicative function. So this is the first theorem, that mu n is a multiplicative function. Proof. Let a and b be any two natural numbers such that their GCD is equal to 1. Because for multiplicative function, we must have AB is equal, GCD is 1, and then we will show that mu AB is equal to mu A into mu B. So let us see mu AB. So there are two possibilities. Either mu AB is 0 or it is not 0. So case 1, mu AB is 0. Mu AB, it is not comma AB, it is product. Mu AB product. So mu AB is 0. That means AB is not square free, because it is 0 if and only if it is not square free. So this means AB is not square free. That means some p square, some prime square will divide AB. Some prime square will divide AB. So there are further now two possibilities. One possibility is that this means P divides A, P divides B, and the second probability is P square divides A or P square divides B. This is one possibility, and this is second possibility. But the first possibility is being ruled out. It is not possible. Why? Because if P divides A, P divides B, then P must divide their GCD. That means P divides 1, because GCD of A and B is 1. So P divides 1 is not possible. So that means this possibility is ruled out. This is not possible. So that means P square divides A or P square divides B. If P square divides A, then A is not square free. And if A is not square free, that means mu A is 0. Or if B square divides B, that means B is not square free. And if B is not square free, mu B will become 0. So either if mu AB is 0, then either mu A is 0 or mu B is 0. In either case, if it is 0 or if it is 0, in both the cases you get mu A into mu B is equal to 0. Mu AB is equal to 0 gives you mu A into mu B is also equal to 0. So mu AB is equal to mu A mu B in this case. It is the first case we have discussed. If mu AB is 0, then mu AB is equal to mu A into mu B. Now look at the other case. If mu AB is not 0, so it is not 0 means it is square free. It is square free means in AB, no prime factor is repeated. So AB can be written as P1, P2, PR, Q1, Q2, Qs, where A is this part and B is this part, and no prime number will be repeated, because even if one of the prime numbers is repeated, it is not square free, and if it is not square free, the value will become 0, but it is given that in this case that the value is not equal to 0, so it is square free, and hence no prime number will be repeated either in A or in B, and no prime number of A can be same as prime number of B, because GCD of A and B is 1. So this is the case now. In this case, what is your mu AB? Your mu AB is minus 1 raised to the power number of factors here, and the number of factors here is clearly r plus s, so it is minus 1 raised to the power r plus s, which can be broken as minus 1 power r into minus 1 power s. But what is minus 1 power r? If you look at this number, this is the value of A. A has r distinct factors, distinct prime factors. So mu A is equal to minus 1 power r. So minus 1 power r can be written as mu A, and similarly minus 1 power s is mu B. So in that case also, in the second case, when mu A B is not 0, in that case also mu A B is equal to mu A mu B. That means whatever the case is there, mu A B is coming out to be mu A into mu B if A and B have GCD 1, and that makes the function mu a multiplicative function. So this is the first theorem related to Mobius function, that the function Mobius function mu is a multiplicative function. Now we move on to the next theorem. The next theorem says for Mobius function mu sigma mu d, where d divides n, is equal to 1 if n is equal to 1, and 0 if n is greater than 1. So we will prove both the cases, when n is equal to 1 and when n is greater than 1. So let us move on to the proof now. In proof, first we will consider the case when n is equal to 1. If n is equal to 1, the left hand side will become sigma mu d, where d divides 1. And how many divisors you have for 1? You have only one divisor, 1. So this is equal to mu 1. And by the definition of Mobius function, mu 1 is equal to 1. So the first part, that sigma mu d divides n when n is equal to 1 is being proved. Now we will move on to the second part. The second part says that your n is greater than 1. Your n is greater than 1. So let n be equal to p1 power alpha 1, p2 power alpha 2, and so on, r power alpha r be the canonical form of n by using fundamental theorem of arithmetic, and it is a unique expression in which n can be expressed. Now if your n is this, the left hand side is sigma mu d, where d divides n is equal to, what you have to do now, you take one by one all the divisors of n, put their values here, mu of that, and then take sum. The smallest possible divisor is 1. So first of all you put d is equal to 1, you will get mu 1. So it is one divisor plus. Now second case, the divisors of the type prime power 1. That means P1 is a divisor of n, P2 is a divisor of n, P3 is a divisor of n, PR is a divisor of n. So you take the terms of the type sigma mu pi, and I vary from 1 to r. Or you can simply say sigma mu pi, where pi divides n. Simply, very simply. plus. Now you take divisors made up of product of two primes. That means sigma mu pi pj, where pi pj is a divisor of n. Earlier I have taken the only prime numbers, either p1 or p2 or p3 or pr. In the next case I have taken divisors of the type p1 p2, p1 p3, p2 p3, p4 p5 of this type, plus and so on. Now take product of three prime numbers p1 p2 p5, p2 p4 p7 of this type, and so on and so on. You will move them up to the place sigma mu, the product of the primes in pair of R, that means all the primes. So it is p1 p2 and so on pr, where each pi divides n. Yes, there are more divisors, but I am not going to take them. Why? Because if you take more divisors, now the divisors will be of the type where prime numbers will occur with powers more than 1. That means p1 square, p1 cube, p1 power 4. And in that case, the number mu of p1 square. Now p1 square is not square free because p1 square itself is a square number. Mu of p2 cube. Once again it is 0 because p2 cube is divisible by p2 square and p2 square is a perfect square. So for all the rest of the divisors of n, the value of the mu will become 0. So I am not taking those all. It is enough to consider this sum. So what it is now? Mu 1. We know it is 1. Now sigma mu pi. It is mu pi. Only one prime number is there. So what will be the value? Minus 1 raised to the power 1. Minus 1 raised to the power 1. But how many terms will be here? You can have here p1, you can have here p2, you can have here p3, you can have here pr. So total possibilities are r. So this term will contain r times minus 1 power n, 1, plus. Move on to the next now. In this case, you are having mu of pi pj, product of two primes. So product of two primes means mu, value of mu is minus 1 raised to the power 2. And how many terms will be here? You are having product of pair in 2 and total possible prime numbers are r. So how many possibilities are here? It is rc2. Similarly, you will have rc3 minus 1 cube and so on. You will have rcr minus 1 power r in this case, the last one. And if you look at it carefully, it is nothing but 1 minus 1 raised to the power r. It's binomial expansion. And 1 minus 1 is 0, so 0 power r is 0. So that means if your n is greater than 1, the value of sigma mu d where d divides n comes out to be 0. And so the second part is being proved. So this is the proof of this theorem. And now we are moving on to another theorem, another important theorem from point of view of examinations, from point of view of understanding the Mobius functions. The theorem says, prove that phi n is equal to sigma mu d into n upon d, where d divides n. What is mu? You know it very well that it is Mobius function. What is phi? In previous videos we have defined phi. Phi is the Euler-Stoichid function, and phi n means the number of natural numbers less than n which are coprime to n. First of all, you look at the function phi n carefully. So phi n can be written as sigma 1 upon GCD of nk box k vary from 1 to n. It is not difficult to understand this. Suppose your n is 10. It will make you clear. I am giving an example which will make you very clear why this is so. Suppose your n is 10. So what is your phi 10 then? According to this rule, it is sigma k vary from 1 to 10 box means greatest integer function 1 upon GCD of 10 and k. So what you have to do? Put k is equal to 1 here, put k is equal to 2 here, put k is equal to 3 here up to 10 and then take their sum. Okay. If you put here 1, GCD of 10 and 1 is 1. So 1 upon 1 is 1 and greatest integer function of 1 is 1. So 1 plus. Now put k is equal to 2 here. When you will put 2, so 10 and 2, GCD is 2. So 1 upon 2 is 0.5 and 0.5 greatest integer function is 0. So it is coming out to be 0 if you put k is equal to 2. If you put k is equal to 3, 10 and 3, GCD is 1. 1 upon 1 is 1 and greatest integer function of 1 is once again 1. If you put k is equal to 4, 10 and 4 GCD is 2. Once again 1 upon 2 is 0.5 and greatest integer function of 0.5 is 0. Plus, put k is equal to 5 now. 10 and 5 GCD is 5. So 1 upon 5 is 0.2 and box of greatest integer of 0.2 is once again 0. Plus, put k is equal to 6 now. GCD of 10 and 6 is once again 2 and 1 upon 2 is 0.5 and greatest integer function of 0.5 is once again 0. Plus, if you take k is equal to 7, GCD of 10 and 7 is 1, 1 upon 1 is 1 and greatest integer function of 1 is 1. Similarly, if you put here k is equal to 8, the GCD will become 2, 1 upon 2 is once again 0.5 and greatest integer function of 0.5 is 0. For k is equal to 9, 10 and 9 GCD is 1, 1 upon 1 is 1 and greatest integer function of 1 is 1. And if you take k is equal to 10, GCD of 10 and 10 is 10, 1 upon 10 is 0.1 and greatest integer function of 0.1 is once again 0. So what the value you are going to get is 1 plus 1 plus 1 plus 1. So it is 4. And you will get 1 every time the GCD is 1. Here you were having the number 1, here you were having the number 3, here you were having the number 7, here you were having the number 9. And in fact these are the numbers less than 10 which are co-prime to 10. And whenever you are having a number less than n co-prime to the number n, you will get 1, otherwise you will get 0, and that means what you are going to get is the number of natural numbers less than n which are co-prime to n, and that is nothing but the value of phi n. So phi n can be expressed in this way. So I think it is very much clear now that phi n can be expressed as sigma k vary from 1 to n box of greatest integer function of 1 divided by GCD of n and a k. Okay, now I am moving on to the second function. The second function is mu. Note that your mu d can be written as box of mu n, you can say mu n. Your mu n can be written as 1 upon n. I should write here mu d sigma d divides n. This is equal to this. Why? Once again, the question is why. If your n is 1, then 1 upon 1 and the greatest integer function is 1. And if n is greater than 1, 1 upon something greater than 1 is 0 point something and greatest integer function of 0 point something is 0. So that means this result is nothing but 0, it is 1 if n is equal to 1 and 0 if n is greater than 1. And this result you have just proved now. So this result can also be written in this form. So I have written this in this form. So I have defined phi n and sigma mu d divides n in a different way. So now look at what can be done to prove this result. Sigma mu d is expressed in this form, phi n is expressed in this form. Look at in this second result, replace your n by GCD of nk, both sides. So here you will get GCD of n and k, and here also you will get GCD of n and k. And the value of this term, greatest integer of 1 upon GCD of nk, this value you substitute it in equation number 1. So equation number 1 will become phi n is equal to sigma k vary from 1 to n, and for this you substitute this value sigma mu d divides GCD of nk. Okay, and now I'm rubbing these two steps because no more I'll need these two formula now for this theorem. I may need space to write more steps, so I'm rubbing these steps. Now look at here. D divides GCD of n and k, and if D divides GCD of n and k, it clearly means D divides n and D divides k. D divides n and D divides k. It is very much clear. So D divides n and D divides k. I am writing here only D divides. I am writing here only D divides, and this I have used. This I will use. How to use this? D divides k means k is some integral multiple of d. That means k is some integral multiple of d, and your k lies between 1 and n. Your k lies between 1 and n. So substitute value of k from here. K is equal to dq. Put it here. So you will get dq here, and multiply this throughout by 1 upon d. 1 upon d is a positive number because d is a positive divisor. So multiplying you will get 1 upon d is less than or equal to q is less than or equal to n upon d. And if d is greater than or equal to 1 upon d, then definitely dq is greater than 1 also. So the second summation, here you are having two summations. The second summation I am taking as q, this q varying from 1 to n upon d. N upon d. And what the term you are having is mu d. Mu d. Now, in the next step, this is the value of, this is coming out to be the value of phi n. So I am writing here phi n is equal to, and now it's very simple step now. Here the summation varies over q, but the term does not contain q, so put it into 1 and take mu d outside. So you will get sigma mu d sigma q vary from 1 to n upon d 1, and here d divides n. Okay, the last step, sigma d divides n mu d. And what is this? Suppose you are having sigma k vary from 1 to 3, 1. So what you will get? 1 plus 1 plus 1 3 times. So it is 3. That means this will be the answer. So similarly here what will be the answer? N upon d. So it is into n upon d. So your phi n comes out to be sigma d divides n mu d n by d, and that is what the result we wanted to prove. So here is a very important theorem, is a very important result which will be used in future theorems, in future lemmas, in future results, in future questions. And one more important theorem I like to prove here in this video, and this is nothing but very important theorem known as Mobius inversion formula. Mobius inversion formula. This formula I will prove here, and we will use it later on in many theorems, in many lemmas, in many questions, in many typical and interesting questions results. So let us see what Mobius inversion formula says. If small f and capital F are multiplicative functions such that capital Fn is sigma Fd d divides n, means the sum of f of divisors of n, then here you have the value of capital F in terms of small f, and it is inversion formula. That means what you want the value of small f in terms of capital F. So what is the value? It is given as small fn is equal to sigma mu d capital F n upon d, where d divides n. So if capital F has this value in terms of small f, then small f has this value in capital F, and that's why it is called as Mobius inversion formula. There are two reasons. Inversion because small f, capital F, small f, capital F, the reversed. Mobius because here you are having no Mobius function, but the inversion you are having the Mobius function. So why it is called Mobius inversion formula. So now let us move on to the proof of this Mobius inversion formula. What we want to prove, I am going to start with the right hand side. That means sigma mu d capital F n by d, where d divides n. This is given to us. Okay, what to do here? This fn by d, fn you have this value. Use this formula here. Use this formula which is given here in this term. So what you are going to get, this term will be as it is, sigma mu d d divides n, and here in place of n you are having n by d. So here also you will have to change because this d and this d will be big confusion. So change this d to k. You can say this is k divides n fk. It's not going to change any value. So use this formula here and replace n by d. So what you are going to get, sigma. Earlier it was k divides n because it was n here, and now it is n by d here. So k divides n by d. K divides n by d. And fk. And fk. Now simply you collect both the sigma together. Sigma d divides n. Sigma k divides n by d. Mu d fk. And now look at this, d divides n and k divides n by d. Here the role of d and k are symmetric. Since the role of k and d is symmetric, they can replace each other. You can have k divides n and d divides n by k. You can write it because D and K are playing symmetric role. So change. Replace D by K and K by D. So sigma K divides N and D divides N by K. The same thing. And now you take Fk because the second summation is over D. So Fk is constant, can be taken out. So you can write sigma K divides N. This Fk will be outside. Fk sigma D divides N by K mu D. Now concentrate on this. Now concentrate on this. You know that the value of this is 0. It is 1 if and only if your N by K is equal to 1. Otherwise it is 0. So you will have only one term here and that is equal to 1. And when that 1 will be there? When your N upon K is 1. And N upon K is 1 means N is equal to K. So this term will become 1. This whole term will become 1 and K divides N will become K equal to N. So in the next term you can write sigma Fk into this whole summation will become 1 and this will become 1 if and only if your N upon K is 1 and N upon K is 1 means your N is equal to K, or you can say K is equal to N. K is equal to N. So Fk into 1 is Fk. So you can write it sigma Fk, K is equal to N. And now you know what to do. You just put K is equal to N here. You will get Fn, and that means the left hand side. You started from the right hand side and you achieved your result left hand side. So if this is given, then the inversion formula, Mobius inversion formula, gives your small fn to be sigma mu d capital Fn by d, where d divides n. So this Mobius inversion formula is being proved. In the next video we will have more and more problems based on Mobius inversion formula, and then I will move on to D polygnat formula, greatest integer function, and I will try to finish this chapter in next two videos. Till then, thank you once again.